My name is Tomáš Jakab, and I will present you our work on self-supervised learning of interpretable keypoints from unlabeled videos. In the recent years, there has been impressive success of computer vision achieved through strong supervision. However, that requires large amounts of labeled data that can be expensive to collect. Hence, we ask the question, how can we leverage unlabeled data, namely object category specific videos, to learn object keypoint detectors? Our approach is based on factorization of appearance and 2D keypoint. This is achieved by training a conditional autoencoder with a tight 2D keypoint bottleneck that encodes the pose information while the appearance is supplied by looking at another frame of the same video. It exploits the fact that the geometry changes, but appearance does not in the videos of the same object instance. The model is trained using reconstruction loss. Similar approach was used in other self-supervised works. However, the disadvantage of this is that the learned keypoint representation of the pose is not interpretable. This means that none of the points will, in general, correspond to landmarks such as the hand, knees, or ankles. We replace the keypoint pose representation with image representation that allows us to use powerful image-to-image translation networks. The pose representation is enforced to follow distribution of skeletons through a discriminator trained on unpaired set of skeletons. While we can now learn interpretable pose representation, we have lost the ability to predict the skeleton keypoints. Further, the image representation can now leak appearance information from the input image, which negatively affects the accuracy of predicted skeletons. To remove the appearance leakage through the skeleton image, we propose a novel autoencoding formulation. The skeleton image is compressed into keypoint coordinates, which are in turn decoded back into a skeleton image using a skeleton image renderer that is based on analytical distance transform. We apply our method to the challenging task of human pose keypoint detection. We learn, for the first time, to directly predict human interpretable landmarks without requiring any labeled images. We also test our method on facial landmarks, where we leverage landmark samples from multi-pi dataset as the prior, and unlabeled images from a large-scale video dataset to train a detector that we test on a standard benchmark. This shows that the method can learn from a prior and images that come from completely different data sources. As previously mentioned, other self-supervised learning methods learn object keypoints that are not interpretable. To compare them on standard benchmarks, they need to learn supervised linear regressor that converts the self-supervised discovered keypoints to semantic keypoints. While our method requires unpaired pose prior during the training, it does not need any labeled images as self-supervised methods, since it can directly predict interpretable semantic keypoints. We outperform the state-of-the-art unsupervised landmark discovery methods on human 3.6 million benchmarks. Please note that these methods discover object landmarks in an unsupervised manner and later train a linear regressor using labeled training data. However, our method does not use any annotated images here. We also outperform all self-supervised learning methods for facial landmarks. The method requires only a small number of unlabeled examples to train the discriminator. The figures show that the keypoint detection performance is not sensitive to the number of unpaired samples and can perform reasonably well with just 50 unpaired keypoint examples. Finally, instead of providing the appearance image from the same video sequence, we use an image from a different identity. The model swaps out the appearance of the original image with the supplied appearance image. This shows that the model factorizes geometry and appearance. The decoder sources geometry from the first frame, while appearance is sourced from the appearance conditioning image. We can also directly manipulate the keypoints to animate images, which can have interesting applications. Finally, I'd like to thank the amazing people that contributed to this project: Ankush Gupta, Hakan Bilen, and Andrea Veraldi. Please see our project website for further information.